Jnanam Paramam Dhyayam. Knowledge is supreme.
In the last lecture, I have stated a fundamental theorem on symmetric polynomials, and we will prove it today, just now. So, let us recall what it is. So, this was the fundamental theorem on symmetric polynomials. This is, some old books also will say it as a Newton's theorem, 1665, 66. Okay. K field, more generally it can be ring also, any ring, any commutative ring, where we can add and multiply elements and so on, and n is a non-zero natural number. Then we are describing the fixed field of fix Sn K polynomial ring in n variables over K. This polynomial algebra is precisely the subalgebra generated by elementary symmetric polynomials. Remember, this notation is the K subalgebra of K x1 to xn containing S1 to Sn, smallest, the smallest. The smallest K subalgebra of the polynomial ring containing x1 to Sn. This is what we want to prove. So, let us start proving. So, for the proof is very simple. So, this proof is due to varying. And this was in the year 1782. The idea is very simple. So, what do we want to prove? We want to prove that every symmetric polynomial is a polynomial in S1 to Sn with coefficients in K. Alright, so for each, I will introduce some notation which will be used in the proof. For each polynomial f in K x1 to xn, a polynomial in K x1 to xn, I can always write uniquely as sum of monomials in x1 to xn and some coefficient. So, a nu, x nu, where this nu is a tuple nu1 to nu_n, which is as natural coefficients. So, this is an element in n power n, and we are using here calculus notation. What is x power nu? X power nu is by definition x1 power nu1, xn power nu_n. That is the definition of this. And when we say degree of this monomial x power nu, this degree is precisely mod nu, which is by definition nu1 plus sum of all nu's, nu_n. That is called a degree. This is the usual, this degree, total degree. So, usual degree of a polynomial is the one where mod nu is maximum. See, this is the finite sum and mod nu is maximum, then that will be the degree monomial, and the remaining monomials will have smaller degree. But I am not going to consider a usual degree. I am going to consider what is called multi-degree. So I will call it MDEG. MDEG of a monomial. There is only one term, so I don't have to define what is MDEG of a monomial. That is by definition nu1 to nu_n. So first of all, let me remind you, multi-degree of a polynomial is not an integer, it is a tuple. So to each polynomial f, I am going to attach an element nu. This nu is an element nu1 to nu_n in n power n. This is multi-degree, and because it will depend on f, I will call it nu_f. And what is it? So that means I have to order this set n power n. So order n power n by lexicographic order from left to right. What does that mean? So let me spell out what is this order. It's order on the set, and how do I compare two elements in that? I have to tell you. So suppose I have two tuples, one is nu1 to nu_n and other is mu1 to mu_n. Both are in n power n. Then I will say nu is bigger or equal to mu if and only if, this is a definition. First I compare their mods. If mod is bigger or equal to, then I will say nu is bigger or equal to mu. But this is a total degree. Either this or it can be equal, and then I start comparing nu1, mu1. If it is equal, also fine. So, but there should be a stage where nu_i should be strictly bigger than mu_i. And then afterwards, I don't care what happens. So, up to here, they are equal, and so that means there exists, in this case, there exists I in between 1 and n such that up to I minus they are equal, and ith stage they are more than the nu is bigger. That is what it means by lexicographic from left to right. You start comparing this. If it is equal, go to the next one, and so on and so on. So this is clearly, this defines order on nu n power n. And now what will, given in a polynomial f, which is the sum like this, finite sum, nu where is in nu power n. So there are finitely many monomials involved, therefore there are finitely many n tuples involved. So I can always decide the biggest one. A finite subset will have maximum, because this is partial order on the set. So therefore I will call multi-degree of f to be the maximum of nu in n power n such that nu should occur here, that means a nu is non-zero. So that is called a multi-degree of f. Multi-degree of f. That is this MDEG f. Now let us give some examples to understand. So for example, if I take S1, this is the first elementary symmetric function. This is x1 plus xn. What is MDEG of S1? This is, see what is this monomial? This is x1. That means 1 0 0 0 0. That is the degree of this monomial. The next one 0 1 0 0 0 0. The xn is 0 0 0 0, last coordinate is n. So obviously this 1 gives the maximum. So multi-degree is 1, 0, 0, 0. And what is the highest degree monomial? That is, so let me write that in general for a polynomial f, we have a multi-degree and there is a highest monomial. So that will be called highest. This is the highest term of f, and this will consist of only one monomial, that is a nu x nu f. This also I call it the mdeg. This where nu f gives the maximum degree. Nu f mod nu f is not mod nu f. Nu f is the degree giving term of f. Okay. So what is the highest term of S1? Highest term of S1 is precisely x1. All other terms will have smaller degree than this, smaller multi-degree, always multi-degree. What about S2? S2 is sum of 2 at a time. So obviously the multi-degree of S2 is 1, 1 because I am taking I naught equal to j in this. This S2 is sum of all terms 2 at a time, product, but the different, not never repeated. So this S2 is sum of these two different variables multiplied together. So therefore the multi-degree is obviously 1, 0, 0, 0 because there is no other term. Any other term will either this is 0 or if this is present, this will be 0 and so on. So therefore it is very easy to see that highest degree term of, so what is h of S2? H of S2 is the monomial x1, x2 and so on. So what will be the, in general, what is the highest, what is the multi-degree of SR? This is precisely 1, 1, 1 R times up to R stage and after that 0, 0, 0. These are R number of terms. And what is the highest degree of, highest term of SR? That is obviously x1, x2 up to the XR. That is also very clear because this is sum running over the tuple I1 less than IR. This is obviously less equal to n, this is bigger equal to 1 and xi1, xi1 etc xir. It's very easy. So highest degree term is very easy. One more example, which is, these are symmetric ones. One non-symmetric example one should see. What is the term? So for example, if I take f equal to x1 cube plus x1 4 x2 plus x2 5. This is my polynomial in 2 variables at least. So what is the degree of this monomial? It is 3, 0. What is the degree here? Multi-degree I am writing. Multi-degree here is 4, 2, no 4, 1. Multi-degree here is 0, 5. x1 doesn't appear, therefore 0 and x2 appears 5 times, therefore this. So who is the highest? I should first see the mod, right? This is mod is 3, this is mod is 5, this is mod is 5. So obviously this will not be the highest degree term. So I have to compare these two, and these two, who is bigger? This is bigger. So therefore multi-degree of f in this case is multi-degree of f equal to 4, 1. What is the highest term of f? That is this one, x1 4, x2. There could be a coefficient here. Suppose it was a here, then the highest degree term will be a here, and this a is in the field K. That is how it was. It is more finer than the degree. because you see, if you ask me what is the degree of f, the degree of f is 5, and this will be the degree term. But when you say multi-degree, then among them also you are comparing, and this is the highest degree of f. So that is the highest degree of term. So what do you want to prove? So we start with a symmetric polynomial, f symmetric, and we want to prove that this symmetric polynomial is a polynomial in S1 to Sn with coefficients in k. That is what we want to prove. Okay. So once I am going to prove this assertion, so we want to prove, what do you want to prove? We want to prove this f equal to g of S1 to Sn, where g is a polynomial in n variable, k I will write for not to get confused, y1 to yn. We want to prove this. We want to find g, so that g is a polynomial in n variables with coefficients in k, so that when I substitute yi is equal to this S1 to Sn, then I get f for some g. And this I am going to prove this assertion by induction on multi-degree. Proof by induction on m degree of f. So where do the induction starts? Let us see. I have given f is symmetric. That means what? That means sigma f equal to f for every sigma permutation. And this sigma f is by definition f of x sigma 1, x sigma n. That means if I permute the variable, f does not change. That is what we have given. So what is the smallest non-zero symmetric polynomial other than the constant? So if f is non-constant, what can be the smallest m degree, m deg f, smallest possible. That is where the induction should start. So what is the smallest possible multi-degree? That will be obviously 1, 0, 0. That is the smallest possible. And obviously this means what? This means what? F is symmetric. So this means, first of all, this monomial x1 appears in f with coefficient. Now once, okay, so I want to prove that the multi-degree smallest possible is this only, because suppose multi-degree of f, suppose this multi-degree of f is nu1 to nu-n, then what do we know? So then, see, I will come back to this. So that means if I interchange x1 and x2, so this means, first of all, this monomial occurs in f, but then because f is symmetric, if I permute x1 and x2, then what do I get here? x1 is going to x2 and x2 is going to x1, this transposition. So this x1, x2, x1 will become x2, this is nu2, x1, no, this is nu1, because x1 has become x2 and x2 has become x1, so this is nu2. Now among these two, the remaining are same. Among these two, I know this is the biggest. Therefore, what is the degree here is nu1 to nu-n, and the degree of this multi-degree of this monomial is nu1, not nu1, nu2 I should write first, that is the power of x1. Nu1, nu2, nu1, etc. same. And this is bigger than that we know. This is bigger because this is a multi-degree. Therefore, we get nu1 is bigger equal to nu2. Now, if I interchange x2 and x3, I will get nu 2 bigger equal to nu 3. So, therefore, if a polynomial is symmetric, what we noted that is multi-degree coordinates will decrease, non-decreasing. So, and where will it start? Therefore, this is the biggest possible, right, among the. So, clearly it can't be, for example, symmetric polynomial can't have any smaller than this degree, multi-degree, non-constant. Therefore, induction will start there, because in this case f has to be S1. So, f, if multi-degree of f is 1 0 0 0, then f has to be S1 only. It can't contain any other monomial, because if it does, then it will not be symmetric. So, it has to be S1. Okay, now therefore I want to, so given f, I want to find g from this f. I want to find g, so that g remains symmetric, but the multi-degree drops, and then the induction hypothesis I want to apply. So, this is symmetric, multi-degree f is, let us say, nu 1 to nu n, and highest term of f is some constant times x1 nu 1 xn nu n. From here I want to find nu g. So, what the property should be? G should be symmetric, and multi-degree of g should be mu 1 to mu n, and this should be bigger, strictly bigger, this, and then I will apply induction hypothesis here, because then induction hypothesis will tell you this is a polynomial in S1 to Sn, and then I will find what is the relation. So, what other thing I will need? That some symmetric polynomial. So, let us see what is this process. So, what I am going to do is the following. It is very simple. So, I have f given here. F is some constant x power nu 1 to nu n, no, x power x1 nu 1, x2 nu 2, etc., xn nu n, plus lower degree terms. Let me write lower multi-degree terms. Multi-degree terms, and I want to find a symmetric polynomial whose highest degree term is this, and cancel it, right. So, what I am going to try. So, first note that because this multi-degree of f equal to this nu 1, nu 2, nu n, we observe that because f is symmetric, symmetry will imply nu 1 bigger equal to nu 2 bigger equal to nu n. This is what we observed above, because it is symmetric. This one, if I permute x1 and x2, I get this. If I permute x3 and x3, I get this, and so on. Now, I look at S1 power nu 1 minus nu 2, S2 power nu 1 minus nu 3, and so on. Sn minus 1 is nu n minus 1 minus nu n, and Sn power nu n. This is obviously symmetric polynomial, because this is elementary symmetric functions and the powers. So, all these are symmetric. So, this product is symmetric. Product of symmetric polynomial is symmetric. All right. So, I am going to subtract this from f. So, f minus this I am going to do. and I want to claim that whatever this I want to call it G. This is my G, and I want to claim that the highest degree term I have cancelled. So, what is the highest degree term here? That is this we know, and I want to compute the highest degree terms here, right. So, they should have the same multi degrees, and when they should have the different coefficient. So, what is the highest degree term here? Highest degree term of S1 is x1, but then power. So, higher degree term of the power is power of the highest degree term. So, this is nu1 minus nu2. What is the highest degree term here? Is x1 x2, and the power of that, which power, is nu2 minus nu1 nu3, and so on. So, here for example, here what will be x1 to xn minus 1 and the whole thing power to nu(n minus 1 minus nu(n) times xn. So, this is the last one is x1 to xn whole power nu(n). So, this is the highest degree term of this polynomial. So, what is this? When I simplify this, what do I get? So, I will collect the powers of x1. x1 power, here it is nu1 minus nu2, here it is nu2 minus nu3, here it is nu(n) minus nu(n), and here it is nu(n). So, successive terms will get cancelled, this nu2 will get cancelled here, nu3 will get cancelled here, and so on. So, what will I get? x1 power nu(n), because this term will getting cancelled with this one, this will get cancelled with this one, this will get cancelled, and so on. So, only nu1 comes, nu1 remains. So, what about x2? x2 power, there is nothing here, here it is nu2 minus nu3, here it is. So, again this nu3 will get cancelled there, so on. So, this will be nu2, and so on. This will be xn power nu(n) at the last, because this is only one coming here. So, we have checked that the highest degree term of this which I have subtracted is this, and higher degree term of this is precisely, so I have to write coefficient A here, so that it get cancelled. So, highest degree term of f minus this get cancelled, and whatever remains is lower degree terms. But that means what? That means I have checked that f minus a s1 nu1 minus nu2 etc. Sn power nu(n), this is equal to G, and this is symmetric, therefore G is symmetric. So, with G symmetric and highest degree term of G or multi degree of G is strictly smaller than multi degree of F. So, by induction the G will be equal to some polynomial H evaluated at S1 to Sn, where H is a polynomial in n variables with coefficients in k. But then F will be equal to this one, A S1 power nu1 minus nu2 etc. Sn power nu(n) plus G, but G is this. So, this belongs to the elementary symmetric, this belongs to the subalgebra generated by S1 to Sn. So, that is what we wanted to prove. So, that finishes the proof of this. I will just show you what we proved it. We proved this equality, because this is obvious, and we have taken an element here and we proved it is here. Therefore, this finishes the proof of the fundamental theorem on symmetric polynomials, and this is very easy proof. The only idea is you define a multi-degree, and next time now I will deduce consequences from here, which will also be very useful for defining discriminant, etc. Thank you.